This is Patrick O'Shaughnessy, and I will be discussing statistical analysis techniques in this module associated with the InTERACCT series. In this third part of the module, we'll cover log transformations and their importance to exposure assessments. There are two learning objectives for this part. One is to be able to demonstrate the importance of applying a log transformation to exposure assessment data, and the other is to understand how to determine an exceedance fraction. As was introduced in Module 6, we have to get back to the concept of a skewed distribution. Because exposure measurements are often skewed, they are, first of all, you could say trapped near the low end by 0. They can't get less than 0, so you can't have a balanced normal distribution, for example, that may go into negative numbers. The excursions then are typically those towards the high end, and so exposure data often has a mode of a certain value, but then larger values will contribute to a tail that moves off towards the right as shown in the histogram here. A special type of skewed distribution is called the log normal distribution. In this plot, I have taken the histogram of the distribution you just saw, and instead of creating bins relative to their actual values, I created bins of the logs of their values. You can see that on the x-axis here, and you can see now that the skew is not very pronounced. In other words, the distribution has a more balanced hump shape of a normal distribution now. Therefore, when using the logs of the concentration values results in the log values having a normal distribution, then we can say that the original distribution is log normal. Here are plots of an ideal scenario of the distribution of counts of airborne particles by size in micrometers. The top plot shows a skewed distribution with a mode, the most frequent number, of 5 microns, and a distribution that slopes to the right, with some particles even as high as 80 micrometers in size. Now, if the x-axis is given a log scale, as shown in the lower plot, which is a graphical transformation instead of applying a numerical transformation, as was just discussed, you see in the lower plot that the distribution has become normal. Again, when that occurs, we can say that the logged values constitute a normal distribution, and then can use all the properties of a normal distribution on the logged values, and then transform them back to their original units. And an example will be given later to help explain this concept. To indicate the central tendency of a log distribution, you might imagine that the average is probably not going to be adequate because, as mentioned in Part 1, the largest values push the mean out towards the right in order to balance them relative to the lower values. Instead, the geometric mean is more appropriate, which happens to be numerically equivalent to the median. For example, back to house prices, the median house price is used to avoid the problem of using the average. And so like the median, the geometric mean splits the distribution in half. 50% of the diameters in this case are lower than it, and 50% are higher than it. Now, a measure of the variability of the values that are log normally distributed is also different than when dealing with a normal distribution, which of course uses the standard deviation to express that variability as discussed in the first part of this module. Now, as shown in the skewed distribution plot here, it doesn't make sense to think about a standard deviation that is balanced on both sides of the mean. So we cannot use the classic standard deviation to report variability. Instead, we are going to use what is called the geometric standard deviation. And oddly enough, it is a unitless parameter, and therefore it's inappropriate to report a geometric mean plus or minus the geometric standard deviation. Recall that the data values are log normally distributed, but if they are log transformed, then those logged values have a normal distribution. Therefore, we are back to using the average and standard deviation to compute the central tendency and variability of the logged values. That's easy enough to do in Excel, where the data values are in a column, and then in the next column over, perhaps the log function can be used to convert them all to their log value. Then you can use the average function to determine the average of the log values and the standard deviation function to calculate the standard deviation of the log values. Then to compute the geometric mean, assuming you transform them using the log base 10, then you simply apply that average as the exponent to 10, as shown here. Likewise, 10 to the standard deviation, s, will give you the geometric standard deviation. Admittedly, this is a bit more complicated mathematically, but it's easily computed in Excel. And then note that Excel does have a function to compute the geometric mean, called geomean, but oddly does not have one to directly compute the geometric standard deviation. So if both are desired, you have to use the approach above. To complete the story, so to speak, you may be wondering why the geometric standard deviation is unitless. The answer has to do with the properties of logarithms. Here is an example to explain this. As shown, the average of a set of logged particle diameter values was 0.7. Raising 10 by that number is 10 to the 0.7, which equals 5 micrometers. Then, as just explained, the geometric standard deviation is 10 to the s. But a way to think about it is that the standard deviation can also be computed from the difference between the diameter value that is one standard deviation away from the diameter of the mean value. As mentioned in Module 6, one standard deviation above the mean includes about 84% of the entire distribution. So to compute that difference for a log normal distribution, the log of the diameter value at 84% is subtracted from the log of the value at 50%, which is the geometric mean as shown in the equation. Now, due to a convenient property of logs, this subtraction is identical to a division as shown. And then, because all the terms are logged, they can all be converted back to their natural units as shown in the lowest equation. And there we can see that a ratio is formed for which units cancel each other, and therefore the geometric standard deviation is unitless. This unitless GSD brings up another question, which is how can you interpret its value? And a way to answer that question is to think about the extreme situation in which the GSD is equal to 1. In that case, the diameter value, here represented by y, at 84% must be equal to the diameter value of the geometric mean, so that that ratio of the two is equal to 1. And that can only happen if all the diameters are exactly the same. The distribution is essentially a spike at one diameter value. And that's really impossible in the real world to have, say, every particle diameter exactly the same as every other one. But some examples include, say, these polystyrene latex spheres that are fabricated to be almost exactly a given diameter for calibrating particle sizing instruments. And in the natural world, a spherical pollen grain from a tree has also been shown to have very close diameters one to the other. And it's called a monodisperse distribution as versus a wider polydispersed distribution. Therefore, as the GSD approaches 1, the skewed distribution is narrowing to a very narrow distribution. Then if 1 is the limit on one end, how big can the GSD get? And the answer is typically up to about 4, which means the value at 84%, when you think about it that way, is 4 times higher than the value of the geometric mean, given that ratio shown above. Most GSDs in nature, for example, exposure concentrations or particle diameters occur within a range of 2 to 4. To visualize the differences, 3 plots are shown here, all with a geometric mean of 5. The upper plot is a distribution with a GSD of 1.1, and you can see that it's very narrow. Then in the middle plot, there is a distribution with a GSD of 2. Again, that's fairly typical. And then in the bottom plot is a distribution with a GSD of 4, which again would be at about the extreme end of a log normal distribution of values measured out in the real world. Now, to use this information, we could consider the concept of an exceedance fraction. Essentially, an exceedance fraction is the percentage of workers that are breathing a compound at levels that exceed an occupational limit. Note, however, that the exceedance fraction is related to the distribution of all the measurements, not the distribution of the means as we talked about earlier. An example will help to understand this concept. Shown here are measured concentrations that are normally distributed to start this example with the simpler situation. Let's say we have a similar exposure group of 15 painters measured for volatile organic compound or VOC exposures over 8-hour time periods. The concern was whether the exposures were acceptable relative to a limit of 100 ppm. Utilizing the histogram feature of Excel as described earlier and given the sorted data shown in the column to the right, we ended up with a distribution that looks very normal. From the descriptive statistics output that we also talked about earlier, we found a skewness value of 0.008, and again where 0 is perfectly normal, and so that also confirms that the distribution is normally distributed. We can see that the two bins labeled 100 and 110 have a total of 3 workers in them. But as noted in the left box, only 2 workers are over 100 parts per million, because the bin labeled 100 contains any values over 90 and up to and including 100. So you can see that bin contains 93 and 100. So only one of those 2 is over 100. Regardless, with 2 workers exceeding the 100 part per million limit, we can do the simple division of 2 out of 15, which is 13%. Therefore, we could say that the exceedance fraction is 13% of the workers. However, it is more accurate to think about the idealized normal distribution of the population of workers. In that case, we can compute an average of those 15 values, which is 77.2 parts per million, and a standard deviation of 16.7 parts per million. With those 2 values and the Excel function norm.dist, we can determine the percentage of all values up to 100%, 100 part per million, by putting in the function value 100 for the mean, and then the standard deviation value, and then true, which stands for the cumulative distribution, which produced a value of 0.914, or 91.4% of all measurements will be below 100. Then we simply subtract 100 from 91.4 and end up with a value of 8.6%. So that's the area in the right tail of the distribution, indicated there in blue, above 100, that indicates the exceedance fraction. So the original value of 13% was a bit higher, and that was again a crude estimate, whereas it would be more accurate if we did this sampling over and over and over again, which would more than likely end up with a value somewhere around 8.6% as shown here. Okay, let's take this one step further using a log normal distribution. We have the same sample of 15 workers, except now we ended up with the more realistic situation in which the results are skewed, with most values around 75 parts per million, but several above 100. Notice that the skewness value is 0.87 now, which indicates moderate skewness. So now we have to think about thinking this as a log normal distribution rather than a normal distribution. Notice also that there are now 4 of the workers that are above the OEL. So a crude estimate now is 4 out of 15, or 27%. Let's analyze this from the more sophisticated approach involving probabilities under the curve of the distribution as we did before. First, we need to determine the geometric mean and geometric standard deviation. As we have learned, that involves computing the average and standard deviation of the logs of the values. Just to show that it doesn't matter which type of log transformation is applied, in this case I used the natural log, which resulted in an average of 4.32. The back transformation to calculate the geometric mean in natural units is e to the 4.32, which is equal to 75.3 parts per million. Likewise, the standard deviation of the log values is 0.48, which results in a GSD of 1.62. And just as before, when the norm.dist function was used, we can now use the log norm.dist function by first entering the value up to which we want the area under the curve, which is our limit of 100 parts per million, and entering the average and standard deviation of the logged values, which, as you can see, results in 72.2%. Again, we're interested in the probability of workers above 100, and therefore we end up with 27.8% as the exceedance fraction. This case therefore produced an exceedance fraction using the probability approach that was rather very similar to the one using the crude approach on the previous slide.
This lesson has been created by the Interdisciplinary Training, Education, and Research Activities for Assessing and Controlling Contaminants from Emerging Technologies program, a collaboration of the University of Minnesota School of Public Health, the University of Iowa College of Public Health, and the University of California, Los Angeles Fielding School of Public Health. Funding for InTERACCT is provided by the National Institute of Environmental Health Sciences of the National Institutes of Health. The content of this lesson is the sole responsibility of the developers and does not necessarily represent the official views of the National Institutes of Health.